Okay, if you recall from the last lecture, we talked about this reaction, the elimination reaction of alcohols to form alkenes, and this is the dehydration reaction. So if you remember, this process is an acid-catalyzed process requiring a lone pair oxygen to be protonated by an acid catalyst that generates a protonated oxonium species. And the reaction mechanism, particularly if this is a secondary or a tertiary alcohol, undergoes an E1 elimination reaction mechanism. That is, we protonate the OH first, and then this can come off as a molecule of water. This forms a carbocation. And again, the formation of this carbocation depends on the ability for groups such as these R groups to stabilize that carbocation. The primary alcohol that I've shown at the beginning generally is more difficult to do this way. But if this carbocation can be formed by having stabilizing alkyl groups, one or two of them on there, or three, primary, secondary or tertiary substrates will do this best, then the anion generated from the acid, if it's HA or water, for example, that can pull off the proton to regenerate our acid catalyst. At the same time, the double bond is formed by pushing the electrons down to satisfy the plus charge, and that forms our double bond. Again, under acidic conditions, this is an E1 reaction mechanism. You will not, well, the formation of carbocations really can only be done under strongly acidic or even neutral conditions potentially, but certainly not under basic conditions. So if you recall this reaction, there are a lot of aspects to this elimination reaction, this dehydration of alcohols. If we take a look at some of the details of that, okay, come here. Remember that the double bond that's formed, particularly if you have unsymmetric alcohols where you could pull off hydrogens from either side, the beta carbon on either side of the alcohol. If it's not a symmetric alcohol, that would form two different regioisomers. So if you pulled off this hydrogen on the left, that would form the double bond to one of those methyl groups, and so we'd have a double bond at the end of a chain. Or if you pulled off the hydrogen to the right of the alcohol in this particular example, you form the double bond, which is more highly substituted. And those more highly substituted double bonds are formed preferentially. The general rule is that the most stable double bond is the one that's formed the most. It forms the fastest and it forms in the most amount. So our major product will be the most substituted double bond. The same is the case for the second example, where we have hydrogen that I've indicated here as one that could potentially eliminate. This is the beta to the carbon with the alcohol on it. Or we have hydrogens in these positions. If you pull off the hydrogen here and form the double bond, you generate a more substituted alkene, and if you were to eliminate a proton from the position to the left of the OH and form the double bond, that would form the least substituted alcohol. It's formed in, alkene. It's formed in a less amount because it's less stable. This generality that in elimination reactions the reaction favors the formation of more stable double bonds also favors the formation of trans double bonds over cis double bonds. So in this case we have a symmetric alcohol, so it doesn't really matter which side you pull the proton off of because it's an even number of carbons on either side. You generate the same product, but in this case we have the possibility of forming a trans double bond or a cis double bond, and you see you get about a 3-to-1 ratio for those. Again, the more stable, lower energy double bond is the one that's produced in larger quantities. Okay? Okay, if we take a look at this next case here, one other aspect of this E1 mechanism is the formation of carbocations that undergo skeletal rearrangements. So you can see in the example we talked about at the last class that if we protonate this OH group and remove this and form a carbocation at this position, We could eliminate from the hydrogens that are beta to it to form the product I've shown here on the right, but that's only producing about 3%. What can happen if you can form a more stable carbocation is that a alkyl group or even a hydride that's adjacent to it can shift over and move over. So that would be this methyl group here in this position. That would put the plus charge now on the carbon where the methyl group left. And then we could eliminate from one of these two methyl groups here to form this alkene, or we could eliminate the CH to the right of that carbocation to form the more substituted alkene. And so those are the major products, the most resulting from the formation of the most substituted, most stable double bond. So carbocation rearrangements can occur if it forms a more stable carbocation intermediate doing so. If it doesn't form a more stable carbocation intermediate, it's much more difficult to do rearrangements. So this shows the energy and the transition state for that carbocation rearrangement. On the left, you see the secondary carbocation with the adjacent methyl group, showing how its orbital is actually aligned properly to do that. At the transition state, that methyl group is migrating over with its pair of electrons. The p orbital is being formed on the carbon that the methyl group is leaving from. And on the right is the product. It's lower in energy, a more stable tertiary carbocation, which then allows elimination to occur in two different regioisomers from there. Hydride shifts can occur as shown in these two cases. So you could have the case where you have a formation of a primary carbocation, a secondary carbocation. That's a secondary carbocation. Once that's generated, a hydrogen with its electrons can shift over to now form a tertiary carbocation, and then from there elimination could ensue either this direction or this direction to form two different regioisomers. Again, the most substituted one would be formed preferentially. If you have a primary alcohol, you can still protonate it, but generating the free carbocation itself is a little bit more difficult to do. However, the loss of the water molecule can be accompanied by hydride shift, and I left this off here. If you recall from last time, there's actually a hydrogen there, forming a secondary carbocation. So instead of having to form, if this came off to form a carbocation, it would be a primary carbocation. Instead of forming that, as the alcohol comes off as water, the hydride shifts over to immediately form a secondary carbocation. Now, this elimination reaction can be done under other kinds of conditions besides just loss of water. So we've been talking a lot about the acid-catalyzed dehydration of H and OH to produce water as a byproduct. This could also be done to eliminate a molecule of HX, hydrogen halides. So if we have a halogen, those bonds are polarized and suitably weak. Those can also come off under elimination conditions. So similar to an alcohol, this is a leaving group. Alcohols only leave if they are protonated first. Halogens don't need to be protonated to leave, and so the reactions actually occur mostly under strongly basic conditions. One of the aspects of this dehydrohalogenation is that the starting material on the left, the alkyl halide, is lower in energy than the products if you look at the bond enthalpies. And overall, the Gibbs free energy reaction for this is actually uphill in energy. Okay, so reactants to products is going uphill. So how do you get that reaction to proceed? Well, one way is to remove the byproducts of a reaction, so and to provide some heat. And so if we're forming HX, then what we want to do is neutralize the acid that's formed. And we could do that by carrying out this reaction in the presence of a strong base. It changes the mechanism. Under strongly basic conditions, you don't generate carbocations. So there are no carbocation intermediates. Instead, the reaction proceeds via a one-step mechanism where we have a base that pulls off the proton at the same time the double bond forms and the halogen leaves. Okay, so a specific example is shown on the next slide where we can see that if we use chlorocyclohexane under strongly basic conditions, we can generate cyclohexene. By the way, this is a typical way in which we represent organic reactions, where we're not trying to balance the reactions or talk much detail about the reagents and solvents, but we're focused on the organic part. So we have an organic starting material, the organic product. But important in here are these other things. So you see here in red is the sodium salt of ethanol. It's what we refer to as an alkoxide. So this is a strong base. This is a base. It's an O-. It's a base, a relatively strong base. And so that's a reagent in this reaction. Reagent. Okay. What's also listed here, and you'll notice it has a similar structure. This is the sodium salt of ethanol. The reaction is carried out in a solvent to dissolve everything. This happens to be a polar solvent. This is ethanol, the alcohol of ethane. And its job is simply to help dissolve the ionic species and the organic species, bring them together so that they can react in one phase. That solvents help to facilitate reactions in that way. We don't talk a lot about solvents, but they can be important in the progress of various reactions. So what you often see when you're using alkoxide bases is that the solvent has the same general structural features. So ethanol, we use sodium ethoxide. You could do the same thing with sodium methoxide in methanol, or we'll see later various base solvent combinations that we can use. Now this base carries out this reaction by elimination of a proton beta to the carbon-chlorine bond, which I've just highlighted one of them here, and the reaction occurs simultaneously where we pull off a proton, the electrons from the bond form the new double bond at the same time we kick off the chlorine. Since this is all happening in one step, we refer to this as an E2 reaction mechanism. The reaction depends on both the alkyl halide and the base. Okay? Here's a specific example also which shows that the elimination reaction under these strongly basic conditions occurs with the same preferences as our acid-catalyzed dehydration of alcohols. That is, if we have an unsymmetric alkyl halide like this bromide here, if we eliminate a hydrogen from this position and form the double bond there with leaving the bromine leaving group, then we form this particular regioisomer. If we were to pull off instead a hydrogen from this position and form the double bond in this direction, then we form this more substituted, more stable alkene, and you see that that's generated in a larger amount. If we had the option of forming an E or Z or cis or trans double bond, it would favor the more stable one there. So it's just like the dehydration reaction under acid conditions in terms of the preferences for the kinds of products and the selectivity, both in terms of the position of the double bond, regioselectivity, or the stereochemistry of the double bond, cis or trans. Now, this is what's been observed in this reaction is that it's a second order reaction in terms of its reaction rates, in terms of the kinetics of the reactions. What that means, of course, is that the reaction rate depends on the concentration of two species, both the alkyl halide and the base. And that indicates that the base is involved in the rate determining step. And based on our E2 elimination mechanism, and we'll talk more details about that in a moment, you can see why that would be the case. The base pulls off the proton at the same time the double bond is forming, at the same time the carbon-halogen bond is breaking. Now the other thing we notice about this is depending on the strength of the bond to the halogen, the reaction gets faster. So alkyl iodides react fastest. Alkyl fluorides, actually they are very difficult to get any reaction at all under this kind of condition. So the strength of the bond depends on the size of the atom, which affects the bond distance. So the bonds get longer, the atoms get longer, they're more polarizable, and the bonds are weaker. So this is right in line with weaker bonds, faster reactions. So if you want to do an elimination reaction under these kinds of conditions, you want to choose bromides or iodides. They'll be better to do the chemistry than chlorides, and fluorides just won't work. So there's examples of that in terms of the kinetics. Now another way that we have as a tool to probe reaction mechanisms and to provide supporting data for what we propose as a reaction mechanism is shown here on this slide. This is an example of a set of experiments which help us determine whether the breaking of the CH bond is important in the rate determining step. And so if it's a reaction which forms a carbocation first, which is a slow step, and then deprotonation is fast, the rate of the rate of being able to pull off the proton is insignificant because it's much faster than the slowest rate determining step. If, however, it's an E2 mechanism, then the deprotonation step, or the deprotonation, the breaking the CH bond, is important in the rate determining step because it's happening at the same time by being pulled off by the base. So in this case, we can see that comparing the reactions where we use, in one case, hydrogens adjacent to the bromine, and in this case, deuterium adjacent to the bromine, we see a difference in rate. So let me explain this a little bit. You should know, hopefully you know, that we use the symbol deuterium to indicate the isotope of hydrogen, which is heavy hydrogen. That is, of course, the main isotope of hydrogen is H1. It consists of one proton in the nucleus. It has a mass of 1. H2, or deuterium, has a mass of 2 because it has one proton and one neutron. Okay, so it's a heavy atom. We haven't changed the number of protons or the charge, but we've changed the mass. So it's a different isotope of hydrogen. So don't get confused by this D symbol. This is just commonly used. It really means this isotope of hydrogen. So it's, in principle, it's exactly the same as a proton, except it's heavier. And because it's heavier, the bond strength is a little bit stronger. It's harder to break the deuterium carbon bond than it is to break a carbon hydrogen bond. So if you carry out this reaction and the rate of the reaction depends on breaking that bond, you're going to see a difference in rate. The ones with deuterium are going to be slower. And so if you do these two sets of experiments and compare the rate of the reaction, you get a rate constant for the reaction where they're hydrogens and a rate constant for the reaction where they are deuteriums. And if you look at the ratio, what this says is that the substrate with hydrogens reacts about 7 times faster than the substrate with deuterium. That's a significant difference in rate, which indicates that the CH bond is being broken in the rate determining step. That's another piece of evidence to suggest that our mechanism, E2 elimination, is the correct one for this example. Just to give you some idea, this ratio of the rate of hydrogen versus an analogous rate of deuterium for the same substrate, if this ranges from about 1 to 2, it means there's very little involvement of the hydrogen carbon bond in the rate determining step, which indicates it's not being broken in the rate determining step. If it's between 3 and 8, which our example is, it means the CH bond is being broken during the rate determining step. Okay, so we know it's not an E1 elimination because no CH bonds are broken in the rate determining step. It's an E2 elimination. Here's more details of that E2 elimination mechanism. This is all occurring from the same, at the same time. So the base that's present, usually alkoxide, is pulling off the proton at the same time. The electrons flow down to form the new double bond and the halogen leaves. And here is the transition state. If you look at the energetics of this reaction, okay, it's a one-step reaction. Here's the activation energy. This is the transition state. And what I've done here is shown you the structure of what that transition state might look like. This symbol we use to indicate that it's not an intermediate, but it is a transition state which has no finite lifetime. It only exists for an instant in time on its way to becoming something more stable. But you notice here we have a bond forming between the base and the hydrogen. At the same time, the bond is forming between the two carbons. So these are bonds which are forming. And at the same time, we have a bond breaking between the CH bond and a bond breaking between the C and halogen bond. So those are bond breaking. And all of this is happening at once. The result is we have kinetics which are consistent with a one-step reaction where both halogen and base are important. This is involved, and this is involved. And one thing you'll notice, let me clear all these scribbles from the screen for a moment. One thing you'll notice is that for this to occur, the orbitals that are aligned here in those bonds, so you notice we're developing a new pi bond here from those original orbitals. This carbon on the left and carbon on the right, they're becoming sp2 hybridized. So notice that the alignment of the bonds have to be properly aligned in such a way that they're all in the same plane. This is something we refer to as anti-periplanar. So if you look at this Newman projection, this shows the proper alignment for this reaction to occur. If you imagine your eyeball here and you're looking down that carbon-carbon bond, this is what we see down here. What you see in the back is this hydrogen, which is aligned anti to the leaving group. So the CH bond is breaking and the CX bond is breaking. This is what we refer to as a periplanar alignment. Both of them are aligned in the same plane, and they have to because we're developing a p orbital on both of those carbons that have to be aligned up to form the double bond. Your book calls this coplanar, so you might see that listed as a coplanar situation. And in order for this elimination to occur, it has to be anti. So it's an anti-coplanar or anti-periplanar alignment is necessary for this elimination to occur via an E2 mechanism. Okay, so if you take a look at some other ways in which this could be drawn, okay, if you take a look at these, it is possible that these could be a coplanar arrangement, but syn, that is, the groups themselves are aligned with a 0-degree dihedral angle, but notice they are eclipsing, so they are coplanar, but it's what we refer to as syn coplanar. Elimination is very difficult to do under these conditions. If it's twisted and you have the Gauss orientation, right, now these are 60 degrees apart. Elimination is very difficult to happen here because you can't form the double bond between the two carbons from those two orbitals that are aligned in the bonds that are breaking. Only when they are in this anti-coplanar or anti-periplanar arrangement can you then break both of those bonds and form the double bond at the same time. That alignment is absolutely critical for this reaction to take place, and we see that manifest itself in real examples. So if you take a look at this example, the cyclohexane structure that I've shown here has a large group which kind of anchors that into the equatorial position. So we have this big tertiary butyl group and it's equatorial, and we have a bromine which is axial. Okay, this cis isomer reacts 500 times faster for elimination with this sodium tertiary butoxide base than the trans isomer. So if I draw the hydrogens in here for you to see, this is the trans isomer where this is equatorial, the large tertiary butyl group, and the bromine is equatorial. Okay, why does the cis isomer react so much faster than the trans isomer? Well, this is a direct result of the requirement for the hydrogen which is being eliminated on adjacent carbons or beta carbons to the leaving group has to be aligned anti-periplanar or 180 degrees apart. So if you take a look at this bromine on the left, the axial bromine is the only one that can undergo that elimination, because if you look at this bond, which is axial, and then adjacent to that we have two hydrogens on that carbon. This is a symmetric molecule, so it really doesn't matter which side we look at. And two hydrogens, equatorial and axial, on this side. So the only bonds for hydrogens which are anti-periplanar to the bromine bond leaving group, and I'll color that in blue this time. There's the bond which is breaking. And if we look to the adjacent carbon, it is these axial hydrogens which are the ones which are 180 degrees apart. Only those can undergo elimination with our base. So we can see that that's aligned properly in the anti-periplanar or anti-coplanar alignment for that to take place. If, however, you look at the situation in the trans isomer, we know that this is the lowest energy conformation, and the bonds which I'm going to show here in red, the carbon-bromine bond, okay, is not anti-periplanar to these hydrogens. So if you look at the two hydrogens which are axial and equatorial here that are adjacent, the dihedral angle between the bromine and this hydrogen or the bromine and this hydrogen are 60 degrees. As a matter of fact, the anti-periplanar bonds to this carbon-bromine bond that I'm highlighting here are the CC bonds of the ring. Those are the ones which are 180 degrees apart. So there's no way you can undergo elimination from this conformation. The only way this could occur is for this to flip to the higher energy state. So if I draw the ring flip conformation, okay, here's the ring flip conformation. That puts the bromine now from an equatorial position to an axial position. The tertiary butyl group now is also axial. So you can see this is a high energy conformation. That's why it's so much slower than the cis isomer shown on the left, because only in this conformation do you now get an so if I draw, I have two hydrogens here, an anti-periplanar alignment of the hydrogens and the bromine that have to break. That's why this trans isomer is so much slower. Okay, another aspect of this is shown on this little bit more complicated example. This is an interesting example. What I have here is a little bit more complicated cyclohexane substrate, which shows the same requirement and impacts the products and the outcome of this reaction. And I do have a typo on here. This one is carried out at high temperature. I don't remember exactly the temperature, but that's not room temperature. But if we take a look at this isomer on the top, we have chlorine, cis to an isopropyl group next to it, and trans to a methyl group 3 carbons away. Okay? If we treat this at room temperature with sodium ethoxide and ethanol, we see elimination occur. There's beta hydrogens here, and there are beta hydrogens here. Okay? Elimination occurs to give the more substituted double bond by elimination of the hydrogen on top as the major product, and the minor product elimination in the other direction. So we see both products formed as we expect. Okay? But if I take this compound and all I do is change the stereochemistry, I change the chlorine from the top of the ring to the bottom of the ring, in this case below, but don't change the other groups, now I see something completely different. At room temperature, under the same conditions, there is absolutely no reaction. But if I heat this up, I see elimination occurring, but I see only one product. And I only see this less substituted double bond being formed. So it's only eliminating in one direction. Okay? This is easily explained by taking into account the conformations of the molecule. And this is why all the things we talked about at the beginning of the semester in terms of understanding the three-dimensional structures of cycloalkanes, the various conformations and the energy required for the various conformations, and how substituents affect that on a cyclohexane, coupled with now our understanding of how this E2 elimination reaction proceeds, then we can rationalize why we see this different result. And that's shown on the next slide. So if you take a look at that first isomer for this reaction, the top case here, I've drawn the conformations, both conformations. So what you can see here is that in the lowest energy conformation, putting most of the groups in the larger groups in the equatorial positions, this chlorine is already axial. And adjacent to that, to the left and to the right, both of those positions have hydrogens which are 180 degrees anti-periplanar. If we flip to the higher energy conformation, that puts the chlorine in an equatorial position. And now the adjacent hydrogens are not 180 degrees apart. The bonds which are 180 degrees apart are shown here in red. They are CC bonds in the ring. Okay? So it's not surprising that this isomer undergoes elimination readily from this lowest energy conformation to provide a two different products, one from elimination of the right hydrogen and one from elimination of the left hydrogen. However, if we look at the other isomer now, what we see is that the lowest energy conformation has all three groups in an equatorial position. From that equatorial position, the Cl bond to the carbon is antiperiplanar only to CC bonds in the ring. The adjacent hydrogens are not aligned properly to undergo E2 elimination. Only if we flip to the higher energy state do we see that now we have a Cl bond that's aligned antiperiplanar to a CH bond. But only one of them, because of the other group. What happens when you flip, of course, is that this isopropyl group occupies the axial position adjacent. That's the bond antiperiplanar, not the CH bond, that's equatorial. So it can only eliminate in one direction. And since it's a higher energy structure to get there, we need to provide a significant amount of heat to get to that state. So that's why this reaction occurs via that antiperiplanar arrangement and provides different results. Well, clearly an E1 mechanism could be possible. You could envision that happening, but I have to say it will only occur in the absence of strong bases, because you will not form carbocations in the presence of strong bases. Only under neutral conditions or acidic conditions can you form carbocations. If you have substrates which generate very stable carbocations, it is possible for alkyl halides to undergo E1 elimination mechanisms by first formation of a carbocation simply by breaking the carbon-halogen bond, but only on tertiary halides and only in the presence of just solvent, no bases. Okay. In the absence of base, you can see here's an example. This particular example shows that if you simply take this tertiary bromide and heat it up in ethanol without any base present, the observed rate is only dependent on the concentration of one species, that is the alkyl halide. It simply undergoes loss of the bromide to form a carbocation, and then loss of hydrogen or proton to form the two possible regioisomers of the double bond. But again, only if it's a tertiary substrate will it undergo E1 elimination mechanisms and without the presence of a base. If we added strong base to this, you wouldn't need to form the carbocation. The base would pull off the proton at the same time. Okay, I just want to summarize some of the things we've talked about for E1 and E2 eliminations. With alcohols, most of the time we are carrying out the reaction under acidic conditions because the OH bond doesn't break without first protonating the oxygen to make it a better leaving group. And under those conditions, it will only do E1 eliminations to form carbocations preferentially when you have tertiary alcohols or secondary alcohols. It is possible to do it by an E2 elimination with a primary alcohol, but you still need to protonate the OH first. But under some rare conditions, you may see that occur where the proton comes off at the same time the OH2 group is leaving. In general, eliminations produce the more substituted alkene because they're more stable. The same is true for trans double bonds or over cis double bonds. And if you form carbocations under E1 mechanisms, they can rearrange. They can rearrange by shifting over carbon groups or shifting over hydrides with their electrons to put the carbocation on a different carbon. Again, that will only happen if it generates a more substituted, more stable carbocation. For alkyl halides, the best way to do this is to use a strong base, and so E2 eliminations are dominant. Whether it's primary, secondary, or tertiary, it doesn't really matter because what's most important is the ability of the base to take the proton, which is on a carbon adjacent to that tertiary carbon. E1 mechanism could be possible with tertiary halides if there are no strong bases present. So the substitution for E2 doesn't necessarily depend or influence the mechanism that much under the presence of strong base because, again, we're not forming that carbocation. But most importantly for E2 eliminations under basic conditions is the requirement for an anti-periplanar or anti-coplanar arrangement of the carbon-hydrogen bond that's being deprotonated and the carbon leaving group bond, which is breaking. Next time we're going to talk about the opposite of elimination reactions. We'll be moving into Chapter 6 and talking about the additions of things to alkenes. So that will be in Friday's lecture.